Welcome back to Operating Systems Crashcast. I'm Victor, and with me as always is Sheila. Today, we're diving into a crucial topic in process synchronization: semaphores. Sheila, are you ready to explore this powerful synchronization tool?
Absolutely, Victor. Semaphores are a fundamental concept in operating systems, and understanding them is key for anyone working with concurrent programming or studying OS internals. Let's start with the basics. What exactly is a semaphore?
Great question, Sheila. A semaphore is essentially a tool used to control access to shared resources in a multi-process or multi-threaded environment. Think of it as a traffic light for computer processes. It was introduced by the Dutch computer scientist Edske Dijkstra in 1965 and has been a crucial tool in operating systems ever since.
That's right, Victor. And it's important to note that there are two types of semaphores: binary semaphores and counting semaphores. Can you explain the difference between these two?
Certainly. A binary semaphore can only have two values, 0 or 1. It's similar to a mutex lock, which we discussed in our previous episode. For our listeners who might have missed that, a mutex is like a key that only one process can hold at a time. On the other hand, a counting semaphore can have any non-negative integer value. This makes counting semaphores more versatile for managing multiple resources.
Excellent explanation, Victor. Now, let's talk about the two primary operations associated with semaphores: wait and signal. In some systems, these are also called P and V operations, respectively. Can you walk us through how these operations work?
Of course, Sheila. The wait operation, or P operation, decreases the semaphore value by 1. If the value becomes negative, the process executing the wait is blocked and added to the semaphore's waiting queue. The signal operation, or V operation, increases the semaphore value by 1. If the value becomes non-positive after this, a blocked process is removed from the queue and allowed to proceed.
That's a great technical explanation, Victor. But I think our listeners might benefit from an analogy to really grasp this concept. How about we use a parking lot as an example?
That's a brilliant idea, Sheila. Imagine a parking lot with a limited number of spaces. The semaphore value represents the number of available spaces. When a car enters the lot, it performs a wait operation, decreasing the semaphore. If there are no spaces available, semaphore value is 0. The car waits. When a car leaves, it performs a signal operation, increasing the semaphore and potentially allowing a waiting car to enter.
That's a great analogy, Victor. It really helps visualize how semaphores manage resource allocation. Now let's discuss how semaphores are used in operating systems for process synchronization. Can you give us some examples?
Certainly, Sheila. Semaphores are widely used in operating systems for various synchronization tasks. They can be used to implement mutual exclusion, where only one process can access a shared resource at a time. They're also used for signaling between processes, such as in producer-consumer problems or reader-writer problems.
Those are excellent examples, Victor. It's worth noting that while semaphores are powerful, they do have some potential drawbacks. For instance, incorrect use of semaphores can lead to deadlocks or priority inversion. Can you elaborate on these issues?
You're absolutely right, Sheila. Deadlocks can occur if processes are waiting for each other in a circular dependency. For example, if process A is holding semaphore X and waiting for semaphore Y, while process B is holding Y and waiting for X, we have a deadlock. It's like two polite people stuck at a doorway, each insisting the other go first. Priority inversion can happen when a low-priority process holds a semaphore needed by a high-priority process, potentially causing the high-priority process to wait indefinitely.
Those are important points to keep in mind, Victor. Despite these potential issues, semaphores remain a crucial tool in operating systems. How do they compare to mutex locks, which we discussed in our previous episode?
Great question, Sheila. While both semaphores and mutex locks are used for synchronization, they have some key differences. Mutex locks are binary. They're either locked or unlocked, like a single-occupancy restroom. Semaphores, especially counting semaphores, can represent multiple resources, more like a multi-stall restroom. Also, the process that locks a mutex must be the one to unlock it, while any process can signal a semaphore.
That's a helpful comparison, Victor. As we wrap up, could you summarize the key points about semaphores that our listeners should remember, especially if they're preparing for an interview?
Absolutely, Sheila. Here are the key takeaways. 1. Semaphores are synchronization tools used to control access to shared resources. 2. There are two types: binary semaphores and counting semaphores. 3. The main operations are wait, P, and signal, V. 4. Semaphores are used for mutual exclusion and process coordination. 5. While powerful, incorrect use can lead to issues like deadlocks. 6. Semaphores offer more flexibility than mutex locks for managing multiple resources.
Excellent summary, Victor. That covers the essentials of semaphores in operating systems. Thanks to all our listeners for tuning in to today's episode of Operating Systems Crashcast. We hope this discussion helps you understand the crucial role of semaphores in process synchronization. Until next time, keep exploring the fascinating world of operating systems.